Machine learning technologies have seen great success in computer vision, natural language processing, intelligent systems, anomaly detection, and many more, potentially changing the future war pattern. The 2018 National Defense Strategy has identified artificial intelligence as a critical technology to ensure that the United States wins future wars. However, we have also seen a notable increase in attacks on machine learning systems in recent years. New vulnerabilities have been identified and new attack methods have been developed that can compromise the trustworthiness of machine learning systems. One goal of this MURI project, supported by the Office of Naval Research, is to build trustworthy machine learning systems with high performance, low age of information, and secure against a slew of security and privacy attacks for mission-critical dynamic military IoT systems.
We demonstrate our machine learning attack and defense on a simulated integrated visual augmentation system. A visual augmentation system integrates a camera array and multi-dimension sensors into one device, enhancing the situational awareness and decision-making capabilities for soldiers and remote command centers on a battlefield. We build our demonstration using YOLO version 5, an open-source multi-object tracking algorithm using neural networks, and we demonstrate real-time object tracking from a virtual reality battlefield. The computer used for this demonstration has an Intel 11900K CPU with 8 cores, 3.5 GHz, and an NVIDIA RTX 3080 GPU with 10 GB memory. We also include an Oculus Quest 2 virtual reality headset, achieving a 6 degree of freedom tracking through 4 built-in cameras and movement controllers to map out the virtual reality battlefield. We use 2 monitors to display the real-time images from the VR equipment. The multi-object tracking algorithm shows recognized objects in colored rectangular boxes. The number on the top of each box is the confidence level that the machine learning algorithm has on that object. As shown in the video, the system dynamically simulates the whole OODA loop that tracks the user's movement and recognizes the VR battlefield objects. When not under attack, the system works well, detecting objects in real time with high accuracy.
Adversarial example is a powerful yet stealthy inference phase attack to machine learning systems. Adversarial example works by applying very small but carefully calculated perturbations to the input. Such a modified input, although still looks very much like the original object, can mislead a well-trained machine learning model and fool the system into taking erroneous actions. The fast gradient sign method, FGSM, the basic iterative method, BIM, the Jacobian-based saliency map attack, JSMA, and the Carlini and Wagner, C and W's attack, are the most widely used and powerful AE attack methods. They are all very effective in generating adversarial examples to mislead the model. This video shows the adversarial example attacks on the VR battlefield. The upper left window shows the original input, and we can see that the YOLO algorithm correctly classifies various objects as shown in the colored boxes. The perturbation generated by FGSM, looking like random noise, is shown in the lower left window. When we add perturbations to the original input, an adversarial example is generated, shown in the right window. Although the object still looks like the original object, a truck in this case, with high probability it is misclassified by the YOLO algorithm as something different.
In an IEEE INFOCOM 2021 paper, we propose Manda, a manifold and decision boundary-based AE detector to defend against AE attacks in a network intrusion detection system. The AE detector is placed before the machine learning-based IDS so that stealthy adversarial examples can be detected and filtered before entering the IDS. Our design exploits the following observation. An adversarial example tends to use minimal perturbations to change its class while preserving its original class's attributes. When using a manifold classification, which is particularly good at capturing topological structure of the samples, an adversarial example tends to be close to the manifold of its original class, regardless of which class it is misclassified into, to retain the important properties of its original class. We build our first AE detection criterion. An input is an AE if the results from the manifold evaluation and the victim machine learning model's prediction are inconsistent. Furthermore, adversarial examples tend to be close to the decision boundary of the machine learning classifier. as a result of minimizing the perturbation magnitude. Consequently, the ML model will be unstable on an AE when random noise is added to the AE. Based on this observation, we evaluate the prediction uncertainty on small perturbations of inputs. We build our second criterion: an input is an AE if it has high uncertainty on small perturbations. We combine the two detection criteria and propose Manda, an AE detector that detects adversarial examples and filters them out before entering the machine learning system. For demonstration purpose, we implemented Manda in our integrated visual augmentation system. This video shows that Manda can effectively detect when the system is under AE attack and flag the adversarial examples. Manda was evaluated for network intrusion detection systems. Our results show that Manda is effective in detecting adversarial example attacks in both binary class IDS and multi-class IDS. Manda outperforms the state-of-the-art statistical test model by achieving a higher AUC score and a higher true positive rate at a same false positive rate.
Model poisoning attack is a new class of training time attack. It is effective and powerful, particularly to federated learning. In federated learning, many distributed clients train their own local models using locally available data. The local model parameters are then uploaded to a central parameter server to aggregate a global model. The global model is sent back to the clients to start the next learning iteration. In a model poisoning attack, a malicious client sends carefully crafted local model updates to the central parameter server to poison the global model. Using label flipping attack as an example, an attacker could attach a specific false label to a targeted object and use the poison data to train its local model. Once the poison local model is integrated into the global model, the resulting global model could misclassify the targeted object as its attached false label. In model poisoning attack, an attacker's goal is composed of three parts: poison the model to get target predictions, maintain the overall accuracy, and minimize the distance between poisoned model parameters and benign model parameters. The minimized norm distance makes the attack stealthy. Previous solutions that focus on anomaly detection over model parameters are shown ineffective. We start a novel detection method that looks at the latent space representation of a model in addition to the model parameters. We assume to have a small auxiliary dataset, also known as validation dataset, that includes tens of clean data records. We can get multiple penultimate layer representation, PLR, vectors by feeding the same auxiliary data point into multiple local models. We observe that the benign PLRs follow the same distribution, while the poison PLRs follow a different one. Based on this observation, we designed a robust federated learning system named FLAIR. In FLAIR, local clients submit their local model updates to the parameter server. The parameter server calculates PLRs for each local model using the same auxiliary dataset, then computes the nearest neighbor of each local model using pairwise PLRs distances. A trust score is also evaluated for each local model based on the frequency that the model is selected as the nearest neighbor. The parameter server aggregates the model updates weighted by their trust scores and uses the result to update the global model. Again, we use the developed real-time object tracking system to demonstrate how FLAIR helped to build resilient federated learning models against model poisoning attacks. A properly trained model can recognize various military and civilian objects. For land vehicles, the system can recognize military cars, civilian cars, and tanks. For aircraft, the system can recognize civilian aircraft, military aircraft, and helicopters. We further show that if malicious clients send in malicious local updates, the global model can be poisoned. As shown in the video, the poisoned model will recognize a particular type of civilian cars as military cars. However, FLAIR will minimize the trust scores of the malicious local updates, thus their impact on the global model is also minimized. The trained model is robust against the poisoning attack. The system can correctly classify the objects. The detailed design of FLAIR is presented in an ASIACCS 2022 paper. FLAIR decreases the model confidence of attackers' target label to a close to zero value, diminishing the influence of poisoned model updates. The evaluation demonstrates that FLAIR significantly enhances the resilience of federated learning against model poisoning attacks.
This video is created for our MURI project supported by the Office of Naval Research. Thanks for watching.